Okay, let's unpack this. You know how AI, particularly large language models, seems to be evolving at just, well, an astonishing pace, churning out text, images, code. It's incredible. Really mind-bending stuff. But what if I told you that despite all this progress, we might actually be hitting some invisible roadblocks? That some really promising paths in AI development are maybe being overlooked? Not because they're flawed, but because of a kind of hidden bias in the tools we use to build AI.
Yeah, what's truly fascinating here, and maybe often overlooked, is that this isn't just about the AI's intelligence itself. It's really about the fundamental infrastructure underneath it all. Today, we're doing a deep dive into something called the hardware lottery. It's a concept that honestly makes you question some foundational assumptions about how we're building the future of AI. Our mission today is to shed some light on what this lottery actually is, why it presents a pretty significant challenge, and maybe most importantly, how we might navigate these risks. To ensure a more open, diverse, and innovative future for AI development, rather than sort of accidentally narrowing its potential.
Hardware lottery. Okay, it sounds almost whimsical, like you said, a game of chance. But it clearly has some incredibly serious implications. So to kick us off, when we talk about this hardware lottery, what exactly are we referring to? What's happening kind of under the hood?
Right. At its core, the hardware lottery describes this phenomenon where the early success and, frankly, intense specialization of particular hardware architectures, well, it inadvertently constrains and biases the development of alternative AI approaches. Think about it like this. Certain types of hardware, mainly GPUs, graphics processing units, have become incredibly optimized for very specific mathematical operations.
Okay.
Things like massive matrix multiplications and also the attention mechanisms fundamental to transformer models, the architecture behind most of the big language models today. These specific operations gain an early, almost insurmountable advantage.
Why is that?
Well, it isn't because other AI approaches are inherently bad. It's simply because the hardware infrastructure has been really honed to accelerate these specific operations. It creates what we call a locked-in situation.
So it's like a kind of technological path dependency. Once one type of hardware gets really, really good at a specific task, that becomes the default. The gold standard, even if other, maybe potentially better ways of doing things might exist if we just had different tools, like building a highway just for cars and wondering why bikes can't use it well.
Precisely. You've absolutely hit the nail on the head. That's the essence of it. And this creates a significant bias, potentially promising routes for AI, like, say, very recurrent learning.
What's that exactly?
That involves models continuously looping and refining information over time. Or sparse learning, which tries to mimic the brain's efficiency by only activating a fraction of its neurons. Or even spiking neural networks, designed to communicate more like biological neurons using discrete spikes. All these methods find it incredibly difficult to demonstrate their true value.
Why? Just because the hardware isn't there.
Exactly, because the dominant hardware isn't naturally suited for their unique computational patterns. It's not that these alternative methods are inherently inferior, it's really that the computational tools aren't built to efficiently showcase their strengths. This creates a technological bias that favors the established ways.
That's a powerful and, frankly, a bit unsettling picture. How our tools might be dictating our discoveries. So if we connect this to the bigger picture, this locked-in situation isn't just some academic curiosity for computer scientists, right? What are the significant risks for the future of AI development if we continue down this path? What's really at stake?
Well, the most profound risk, I think, is that it biases our entire exploration space. We end up funneling vast resources, talent, research efforts towards certain types of AI simply because the existing hardware favors them. And this means we might be missing out on entire categories of AI that could be more efficient, maybe more powerful, or even potentially more robust and safer.
Safer? How so?
Well, simply because we haven't given them the right environment or the right tools to truly shine. Think of it like having the perfect soil for growing corn and never discovering that potatoes in different soil could actually feed the world even better.
So we're not just potentially missing out on innovation, but also on the possibility of a better quality of AI, perhaps one that's more reliable or maybe less prone to some of those unpredictable behaviors we hear about.
Exactly. And this ties directly into the broader discussions around emergent abilities in large language models. Our sources for this deep dive include a fascinating CSET explainer, which highlighted that LLMs sometimes possess abilities their developers didn't explicitly program or even predict.
Right, they just sort of appear.
They can appear suddenly, unpredictably, as models scale up. The risk here is significant. Unpredictable, sudden jumps in capabilities, especially if they are dangerous or misaligned with what we want, can arise without enough time for us to develop adequate mitigation measures or even really understand them.
Okay, here's where it gets really interesting and maybe a bit concerning for me. If we're locked into hardware architectures that primarily foster these kinds of unpredictable, sudden emergent capabilities,
Hmm.
aren't we just exacerbating that risk?
Hmm.
We're effectively narrowing our options.
Right.
Yeah. And not adequately exploring architectures that might lead to more understandable, more controllable, maybe more gradual and predictable emergent behaviors.
Yeah.
It feels like we're unknowingly putting all our eggs in one basket, and that basket might have some surprising holes.
This raises a truly important question, I think, for society. If our hardware biases limit the kinds of AI architectures we can effectively explore, we might inadvertently be funneling development down paths that are inherently harder to predict, harder to control, and potentially less aligned with our long-term goals for beneficial AI. The urgent goal, then, is to move beyond just scaling existing architectures,
Yeah.
just making current models bigger towards more fundamentally different forms of AI. These new forms could potentially be less hardware constrained, allowing for a broader range of innovation, and perhaps even be more predictable and interpretable in their development and behavior.
That's a powerful and, yeah, unsettling picture that our tools could be leading us to more unpredictable outcomes.
Hmm.
So the crucial question now becomes, how do we actively counter this hardware lottery? How do we break free from this locked-in situation and explore those alternative, potentially more optimal paths for AI evolution? Paths leading to, hopefully, more predictable and beneficial outcomes.
This is really where the innovation needs to happen. The primary solution involves developing AI architectures and research paradigms that can effectively operate beyond the constraints of current hardware biases. This means a multi-pronged approach, fundamentally rethinking how AI thinks and also how we build its knowledge base.
You mentioned rethinking how AI thinks. Can you elaborate on that? Specifically, you alluded to something called latent space reasoning. That sounds incredibly abstract, almost like sci-fi. Does this mean AI would be thinking in a way that's fundamentally different from how we understand human thought? Or is it just more efficient?
That's an excellent question, and it's really key to understanding this shift. Latent space reasoning directly challenges the token-centric biases of current hardware. So instead of AI always having to speak or output discrete words or parts of words, those individual tokens current language models work with,
Right.
this allows models to think in a more abstract, non-linguistic flow within their internal representations. It's like the AI is doing a lot of deep internal processing, a sort of continuous thought, if you will, before it ever commits to a specific word or output. It's moving beyond just linear token by token stuff.
So it's like the AI is meditating on a problem, chewing on concepts, brainstorming, evaluating multiple solutions in its mind before it ever has to actually articulate a single answer or token.
Hmm.
That sounds like a much richer internal process, maybe more human-like in concept, even if the mechanism is totally alien.
Precisely. And we're seeing this manifest in several quite exciting approaches. First, there's this concept of recurrent depth and reusing layers.
Okay.
This isn't just about adding more layers, but designing models that can perform more iterative computation on the same tokens or repeatedly use the same layers within their architecture. The real takeaway here is we're effectively giving AI potentially infinite depth of thought within existing hardware.
Infinite depth.
Well, think of it as the AI being able to think more deeply about each piece of information, turning it over in its internal mind multiple times before it has to output a word or action. This allows for complex, multi-step reasoning without being forced to output a token at each intermediate stage. It uses existing hardware more flexibly for these iterative internal thought processes. It enables a richness of internal processing that could radically change the kind of problems it can tackle without needing a brand new supercomputer.
That's fascinating. Getting more mileage out of our existing hardware, like giving the AI more time to ponder without needing a bigger physical brain. What's another approach to this latent space idea?
Another really groundbreaking approach is direct latent state feedback. There's an example system called Coconut. This paradigm avoids the constant conversion of rich internal latent representations, those hidden states, basically the model's detailed internal thoughts into discrete tokens. Instead, the last hidden state, which encapsulates a complete continuous thought, is directly fed back into the model as an input embedding.
An embedding.
Yeah.
Remind us.
Right. An embedding is essentially a dense numerical representation. It captures the meaning of concepts, images, even entire intentions in a way AI can process. Now, this isn't just a technical tweak, it's really a paradigm shift. It frees AI from the linear token by token constraints of human language. It empowers the AI to explore and think in complex, multifaceted ways, much like we might brainstorm a solution, weighing many options before articulating one answer. The source material tells us this approach enables emergent, advanced reasoning patterns, like breadth-first search.
Like exploring all possibilities at once.
Sort of, exploring all possible options at one level before moving to the next. It allows the model to consider multiple alternative reasoning steps without prematurely committing to a single path. This bypasses the information loss and the computational expense tied to tokenization, allowing for much more nuanced internal processing.
So this is essentially the AI being able to talk to itself in its own rich internal language of concepts without having to constantly convert it into words and back again. It helps it keep its thoughts continuous and full of detail. That does sound like a significant leap. What's the third approach?
Thirdly, we have large concept models. These models are trained at a much higher conceptual level. They use rich, multimodal embeddings that directly represent intentions and concepts, rather than relying solely on individual tokens. Think about systems like Facebook's Sonar. They create embeddings from various modalities, not just text, but images, audio, sensor data, and even across different human languages.
Wow, okay.
This allows the AI to reason directly with these sophisticated, sort of super language embeddings. The results of this internal reasoning can then be translated back into human language or actions as needed. This lessens the dependence on hardware specifically optimized for discrete token processing. It opens up possibilities for AI that thinks about concepts, not just words. And why this matters for you, the listener, is that it could mean AI that's not just more powerful, but maybe more reliable and capable of understanding complex human intent in a way that's far less prone to the ambiguities of literal language.
Those architectural changes sound pretty revolutionary.
Mhm.
But beyond how the AI itself is built, what about the broader research landscape? It sounds like we also need a shift in our collective research priorities, right?
Absolutely. Beyond just the architectural changes, we also need a broader shift in our research priorities to really cultivate a more diverse AI ecosystem.
What would that look like?
Well, one key area is prioritizing latent space quality and cross-modal integration. Researchers are being encouraged to focus not just on making models bigger, but on enhancing the quality of these abstract latent space representations and improving how different modalities like text, images, 3D geometry, even physics are integrated within these spaces.
Why is quality the key word there?
Because a higher quality latent space means the AI's internal thoughts are more precise, more comprehensive, and more capable of capturing nuanced relationships between concepts. This moves us beyond just scaling up existing architectures towards more fundamentally different and potentially less hardware-constrained forms of AI. It paves the way for truly intelligent systems that can understand the world in a richer, more unified way.
So it's about the richness and depth of the internal understanding, rather than just the sheer volume of data it's processed or the number of words it can spit out.
Okay.
What other shifts in research are crucial?
Another crucial shift is innovating knowledge representation with large knowledge models, LKMs. Currently, models implicitly learn knowledge within their vast parameter sets, the weights and biases. And these are highly coupled with specific hardware architectures. LKMs, however, propose storing and refining knowledge in explicit, persistent, external, latent space information stores. Things like vector databases.
Vector databases, like a super efficient library for AI concepts.
Exactly like that. Think of it as a highly efficient searchable library where every piece of information, a fact, an image, a concept, is stored as an embedding, that numerical vector capturing its meaning. This decouples knowledge from the core model parameters. That allows for easier updates, refinement, and traceability of information, much easier. It also potentially enables more diverse hardware optimization just for knowledge management, rather than just core computation.
So freeing up the main AI model to focus purely on reasoning, not rote memorization.
Precisely. This could lead to AI that is not only more knowledgeable, but also more up-to-date and transparent about where it's getting its information.
That seems like a huge step towards making AI more flexible and, importantly, auditable, separating its knowledge base from its reasoning engine. Okay, so far we're talking about making the most of current hardware or re-architecting AI's mind. But what about entirely new hardware? something that isn't beholden to the biases we've discussed.
Right, that's where exploring alternative computing paradigms comes in. And while it's definitely more speculative, it represents a frontier of immense potential. Investigating entirely new types of computational hardware, like quantum computers, could offer fundamentally different processing capabilities. Capabilities that are not biased towards the operations favored by current classical AI hardware. The whole concept of quantum supremacy, where quantum computers might solve problems classical computers just can't in any practical time frame, could open up entirely new avenues for AI development.
Like what kinds of avenues?
Imagine an AI that can explore vast solution spaces simultaneously, or simulate complex physical systems with unprecedented accuracy. And beyond quantum, researchers are also looking at things like neuromorphic chips, designed to mimic the brain's structure and efficiency, or even optical computing using light instead of electricity. Now, these are definitely long-term bets, but they hold the promise of truly breaking free from the hardware lottery by introducing entirely new rules to the game.
This all sounds incredibly promising,
Yeah.
especially moving into these abstract latent spaces and exploring entirely new computing frontiers. But, and this feels like a big but, if AI is thinking in ways we can't easily see, or ways that are fundamentally different from our own, how do we ensure it's doing what we want and doing it safely and controllably? This seems like a critical trade-off we need to address.
That's a crucial point, absolutely. It's the flip side of this innovation coin, you might say. As AI systems increasingly reason in these opaque latent spaces, developing robust methods to monitor, interpret, and control these internal processes becomes absolutely critical. We can't just, throw solutions at the problem without understanding them. Techniques like meta-reasoning.
Reasoning about reasoning.
Exactly, and AI reasoning about its own reasoning process. Also circuit tracing, where we try to map the specific pathways of information flow within a neural network. And attribution graphs, which help us understand which parts of the input actually contribute to specific outputs. These could provide invaluable insights into how models think without relying on those explicit token outputs. Now, while this doesn't solve the hardware lottery directly, it does mitigate a significant trade-off associated with pursuing latent space reasoning. It helps ensure safety, alignment, and interpretability, even if the underlying computational processes are less, human amenable. It's fundamentally about building transparency and control into these new, less hardware-dependent architectures from the start.
So it's about building the equivalent of a clear window, or maybe even an internal self-reporting mechanism, into these new architectures so we can actually trust what they're doing. Wow, what an incredible journey we've taken today.
Indeed. The hardware lottery isn't just some technical challenge. It's really a fundamental call to broaden our perspective on what AI can be, to look beyond the paths of least resistance, you could say. We've seen how thinking differently about AI architecture, shifting our research focus towards richer knowledge representation, and even exploring entirely new computing paradigms can unlock incredible, currently unseen potential.
So what does this all mean for you, the listener? Well, it means that the future of AI isn't some predetermined path dictated solely by existing technology. It's an active, dynamic landscape of innovation, where challenging fundamental assumptions, like what kind of hardware we build on and how we enable AI to think, can lead to breakthroughs we can barely imagine today, offering AI that is not only more powerful, but potentially more aligned, more predictable, and ultimately more beneficial.
And this raises, I think, an important final question for all of us. As we push towards more abstract latent space reasoning and maybe explore things like quantum AI, how much more human-like, or conversely, how much more alien will AI's internal thought processes become? And crucially, how will we ensure we truly understand and align with intelligences that may think in ways utterly divorced from human language and our current computational biases?
A truly thought-provoking question to leave you with. How will we ensure we can navigate and align with the mind of an AI that thinks in quantum states or abstract latent spaces? That's certainly something to ponder until our next deep dive.